I see that metric lets you pick how you measure the distances between your data points. You could use the usual Euclidean distance, like the straight line distance, or maybe something else like Manhattan distance. Think of walking city blocks. The cool part is that changing the distance metric changes how your data gets squished into a lower dimension. It's like using different lenses to see your data. Think of random_state as the seed for your random number generator. It's like setting the starting point for a maze. If you use the same random_state, you'll always get the same starting point, making your results repeatable. It helps to ensure you're comparing apples to apples when you run the algorithm multiple times. However, remember, even with the same starting point, the number of steps you take, iterations, matters. This is what the smacof algorithm gives you after it's done its magic. It's the simplified version of your data, now in fewer dimensions. Imagine taking a crumpled piece of paper, high-dimensional data, and flattening it, low-dimensional embedding. It might lose some details, but the overall shape and relationships between points should be preserved as much as possible. It's all about finding a good balance. I see max_iter as the number of times the smacof algorithm tries to find the best low-dimensional representation of your data. Think of it like repeatedly refining a sketch until it looks just right. More iterations generally mean a better, more accurate result, but it takes longer to complete. The metric parameter tells smacof how to measure the distance between data points. Euclidean distance, straight line distance, is common, but there are others like Manhattan distance, measuring distance along city blocks. This choice significantly affects the results, as different distance measures may reveal different patterns. I use random_state to make sure that smacof starts from the same random initial point each time. This is important for reproducibility, which means you get the same answer every time you run the code with the same data and settings. However, even with the same starting point, slight variations can happen, depending on the number of iterations. This sets the number of dimensions your data will be reduced to. It's like deciding how many features you want to keep after simplifying. Increasing this parameter doesn't always guarantee better results. You can end up overfitting to the data. I would rather reduce dimensionality to capture only the most important features. I'm analyzing the parameters of the smacof scaling by majorizing a complicated function algorithm, a method used for dimensionality reduction in scikit-learn. I'll focus on how each parameter affects the results. It's like tuning a musical instrument. Each knob changes the sound. These are the settings you adjust in the smacof function to control the process and customize the outcome of the dimensionality reduction. I'm considering 4 key parameters. Think of them as the dials and switches on a complex machine. This parameter specifies the number of dimensions you want to reduce your data to. For example, if your data is initially in 100 dimensions, and you set n_components equals 2, then the algorithm will try to represent the data in just 2 dimensions. Increasing this number doesn't automatically mean better results. It could lead to overfitting. This dictates the maximum number of iterations the optimization algorithm will run through to find the best low-dimensional representation. More iterations generally lead to a more accurate result, because the algorithm gets closer to the best solution at each step, but it will take longer to finish. It's a trade-off between accuracy and time. This parameter lets you choose the distance metric used to calculate dissimilarities between data points. I can select options like Euclidean, straight line distance, Manhattan, city block distance, or others. The choice influences how the algorithm measures the distance between points, and so, it affects how the data is represented in the lower dimensional space. Think of it like choosing different rulers to measure the same distance. You'll get different results. This is like setting a seed for a random number generator. Using a specific random_state value ensures you will start the optimization algorithm from the same initial point each time you run it. This is very important for reproducibility, as you get the same answer every time under the same conditions. However, if I change max_iter, the final result might still be slightly different, as there are small variations in the algorithm's journey towards the solution. I'm analyzing how different settings in the smacof scaling by majorizing a complicated function, algorithm affect the results of dimensionality reduction. Think of it like sculpting. We're trying to create a smaller, simpler version of a complex shape, and different tools and techniques will lead to different results. This is the core question. We're asked to identify which statements correctly describe the behavior of several parameters within the scikit-learn implementation of the smacof algorithm. This algorithm is all about finding a low-dimensional representation of your data that preserves the distances between data points as well as possible. It's like making a map of a country. You want to keep the relative distances between cities accurate, even though you're shrinking the country down. I agree with this. Max_iter controls the number of times the algorithm tries to improve its solution. More iterations generally lead to a more accurate result. It's like polishing a sculpture. You'll get a smoother, better-looking piece with more polishing, but it will take more time. Absolutely. Metric determines how you measure distances between data points. Different ways of measuring distance, like Euclidean or Manhattan distances, will give different results. Just like using a ruler versus walking to measure distance between 2 points will give different answers. I mostly agree. Random_state sets the starting point for the algorithm, which is crucial for reproducibility. Using the same seed, random state, makes sure that you start at the same point each time, improving repeatability. However, it is important to note that due to the iterative nature of the algorithm, slight variations are possible even with the same random state due to the algorithm's inherent randomness. Think of it like rolling dice. You start with the same initial number, but each roll still can be different. This section simply indicates that we're focusing on the adjustable settings or hyperparameters of the smacof algorithm. Here, we're specifically calling out the algorithm at the heart of the problem, smacof. This refers to the final result of the algorithm, a simplified representation of the data in fewer dimensions. It's like taking a three-dimensional object and drawing a two-dimensional picture of it, preserving as much as possible the relative positions of the parts. I see that you are analyzing the effect of the maxiter parameter in the smacof function. A larger maxiter value means the algorithm runs for more iterations. This generally leads to a more refined solution, as the algorithm gets closer to the optimal low-dimensional representation of your data. However, more iterations mean more computation time, so you need to find a balance between accuracy and computational cost. It's a classic optimization trade-off. Here, we're looking at the metric parameter. The smacof function needs to calculate distances between your data points. The metric tells it which distance formula to use, Euclidean, Manhattan, or others. Each distance formula gives different results, so choosing the right one is important for getting the embedding you want. Think of it like choosing the right tool for the job. This focuses on the role of randomstate. In smacof, the algorithm starts from a random initial configuration. Setting randomstate ensures you always start from the same random point, making the results more repeatable. However, remember that the algorithm is iterative. Even starting from the same point, a different number of iterations might cause slight variations in the final result. This title tells us that we're going to learn about how different settings in the smacof, scaling by majorizing a complicated function, algorithm affect how well it squeezes high-dimensional data into a lower dimension. Think of it like taking a complex, tangled ball of yarn and trying to flatten it into a 2D shape while keeping as much of the original structure as possible. smacof is a specific type of multidimensional scaling, MDS, a method used to reduce dimensionality while preserving pairwise distances. We'll focus on understanding the impact of specific parameters on the results. This is a multiple-choice question testing your understanding of the scikit-learn smacof functions parameters, n_components max_iter metric and random_state . Let's see how well you understand each of them. I think this is true. max_iter sets the maximum number of times the algorithm tries to improve the solution. More iterations generally mean a better, more accurate solution, because the algorithm has more chances to find a better fit, but it also means more computation time. Think of it as polishing a sculpture. The more time you spend polishing, more iterations, the better the finish, more accuracy, but it takes longer. I agree. The metric parameter specifies how we measure distances between data points. Different metrics, like Euclidean distance or Manhattan distance, give different results. For example, Euclidean distance is as the crow flies, distance, while Manhattan distance is like walking along city blocks. The choice changes the dissimilarity matrix, which completely changes the final representation. I would say mostly true, but with a caveat. Random_state sets the starting point of the algorithm. Using the same random_state value makes sure the algorithm starts at the same point every time, which helps in reproducibility. However, even with the same starting point, different numbers of iterations might lead to slightly different final results, especially if the algorithm hasn't fully converged. This parameter determines the dimensionality of the embedding space that you want. A higher n_components value means the algorithm produces a representation in a higher dimensional space. This can be good to preserve more information in the dataset, but it can also overfit to noise and become computationally costly. This one controls the maximum number of iterations of the algorithm. More iterations mean a more refined output, at the expense of computation time. This parameter specifies the distance metric used to compare points. Choices such as Euclidean or Manhattan distance can significantly impact results. This parameter controls the randomness in the algorithm. Using a specific number ensures reproducibility. However, because the algorithm is iterative, different numbers of iterations with the same random state might yield minor differences in the final results. I'm asking you to assess your understanding of the smacof functions parameters and how they affect dimensionality reduction. You'll need to determine which statements accurately describe the behavior of these parameters. Think about how each parameter influences the final low-dimensional representation of the data. This statement is true. Max_iter sets the maximum number of iterations the algorithm runs. More iterations generally mean a more accurate result, because the algorithm gets closer to the optimal solution. However, this comes at the cost of increased computation time. It's like repeatedly refining a sculpture. Each iteration improves the final product, but takes more time and effort. This is absolutely true. The metric parameter specifies which distance metric smacof should use when calculating dissimilarities between data points. Different metrics, like Euclidean or Manhattan distance, give different results because they measure distance in different ways. Think of it like using a ruler versus a tape measure to measure the distance between 2 points. The measurements will differ. The chosen metric directly impacts the resulting embedding because it dictates how distances are calculated and optimized within the low-dimensional representation. I'd say this statement is mostly true but needs a little nuance. The random_state parameter is key for reproducibility. Setting a value for random_state ensures the algorithm starts with the same initial conditions every time. However, because smacof is an iterative algorithm, even with the same starting point, a different number of iterations might lead to slightly different final results, especially if the algorithm hasn't fully converged. It's like starting a race at the same point, but even with identical starting positions, runners might reach the finish line with slightly differing times based on their individual paces. Nope, this is false. Increasing n_components which is the target dimensionality, does not guarantee a more accurate embedding. A higher dimensionality might lead to overfitting. It captures noise in the data rather than the actual underlying structure. It's like adding more detail to a drawing. It might be more complex, but not necessarily more accurate or representative of the original image. This row serves as a heading summarizing the parameters we're discussing. n_components max_iter metric and random_state . This simply helps organize information about the options for each of the related smacof parameters. This is the target dimensionality of your reduced data. You choose how many dimensions you want to reduce your data to using this parameter. This parameter sets the maximum number of iterations the smacof algorithm will perform during optimization. This parameter specifies the distance metric used by smacof to calculate the dissimilarities between data points. For example, Euclidean, for Euclidean distance, or pre-computed, if you're providing your own dissimilarity matrix. This parameter controls the random number generator for reproducibility. Using the same random_state value ensures that you'll get the same results each time you run your code, given the same input data and other settings.